The Basel problem. Long ago, I had promised that we will prove that the sum 1 plus 1 by 4 plus 1 by 9 plus 1 by 16 plus so on sums up to pi squared by 6. We have already shown in the chapter on sequences and series that this series converges. But we don't know exactly as of yet what it converges to. Now, there's an interesting story behind why this is called the Basel problem. Basel is a place in Switzerland, it's a city, and it's a hometown of Euler, who finally gave the solution to this problem. Later, Euler generalized his methods. His methods were originally not even fully rigorous, but the gaps in his proofs were later fixed. He has generalized this identity to a much more general one involving what is known as the Riemann zeta function. And his work essentially has consequences for the structure of primes, which was taken up by Riemann, as the name Riemann zeta suggests, and it's one of the most important things that is studied in analytic number theory. Anyway, we will not give Euler's proof, we will give a very modern proof that uses Tannery's theorem. So we want to show that 1 plus 1 by 4 plus 1 by 9 plus dot 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 is pi squared by 6. I'm going to start with a seemingly innocent trigonometric identity and get this. What I'm going to do is I'm going to start by saying 1 by sine squared x is actually equal to 1 by 4 sine squared x by 2 cos squared x by 2. This is just the half angle formulas that you're familiar with from high school. And I just use the fact that sine squared theta plus cos squared theta is always 1 to rewrite this as 1 by 4 into 1 by sine squared x by 2 plus 1 by cos squared x by 2. Okay. Now what we do is we rewrite this as 1 by 4 into 1 by sine squared x by 2 plus 1 by sine squared pi plus x by 2. Again, I'm just using some famous trigonometric identities that you are familiar with. Okay, so we have derived this expression. Now what we are going to do is we have landed up with 1 by sine squared something. We are going to repeatedly apply the identity that we have, that 1 by sine squared x is 1 by 4 1 by sine squared x by 2 plus 1 by sine squared pi plus x by 2. We are going to repeatedly apply this to the point 1 by sine squared pi by 2, which as we all know is just 1. Okay, so at the first stage we get 1 by 4 times 1 by sine squared pi by 4 plus 1 by sine squared 3 pi by 4. Okay, note this observation will become important in the future. Note that the term here is actually just sine squared pi minus pi by 4, right? And we all know that sine squared pi minus x, or rather sine pi minus x, is just sine x. So these two terms are actually equal. These two terms are actually equal, and that's going to play a role now. Now what we do is each one of these terms, 1 by sine squared pi by 4 and 1 by sine squared 3 pi by 4, we are going to expand again by using the same identity. So you will get another 1 by 4, so which I will write it as 1 by 16. Then this sine squared pi by 4 will just become sine squared pi by 8. Okay, plus let me deal with this sine squared 3 pi by 4 term first. So I will get plus 1 by sine squared 3 pi by 8. Then I have two terms coming from the second part of this identity. So what will happen is I will get 1 by sine squared of 5 pi by 8 plus 1 by sine squared of 7 pi by 8. These are the other two terms. Okay, so essentially I'm just applying this identity again and to both these terms. So you will get a pi plus x by 2. That's why you are getting a pi plus pi by 4 by 2, which is 5 pi by 8, and similarly 3 pi by 4, 3 pi plus pi, sorry, I got a bit ahead of myself. You get 3 pi by 4 plus pi by 2, which is going to get you 7 pi by 8. Okay, so I hope I said that correctly. Now again observe that this term is equal to this term, because this is just sine pi minus pi by 8, or rather sine squared pi minus pi by 8. Similarly, this term and this term are equal. Okay, now again each one of these terms I expand once again by using the same fact. So sine squared pi by 8 will just become sine squared pi by 16. Then I'll get a sine squared pi by 8 plus pi by 2, so on and so forth. I will get many terms, and a bit of thought will tell you that the general form of this is just summation, rather 1 by 4 power n summation k running through 0 to 2 power n minus 1, 1 by sine squared 2k plus 1 pi divided by 2 power n plus 1. Okay, so if you want to prove this rigorously, just do induction. Induction proves this rigorously. Alternatively, just observe that each one of these terms will give 2 children, and each one of these terms will give 2 children, 2 children, 2 children. So you will get 8 terms, and you will get all the odd multiples of pi power 2n plus 1 at the 2 power n plus 1 stage. That's what these are. Okay, so you can either, if you are really pedantic, you can just do induction. If not, you can just observe that this is in fact true. Now remember this observation that I said, the first term is equal to the third term, the second term is equal to the fourth term. Well, this holds even in this general expression. So what you need to essentially observe is that you don't need to sum up till 2 power n minus 1. You can stop at 2 power n minus 1 minus 1 and just take a 2 outside. So this is just 2 by 4 power n summation k equals 0 to 2 power n minus 1 minus 1, 1 by sine squared 2k plus 1 pi divided by 2 power n plus 1. Okay, so what I'm essentially doing is, since I know that there are certain terms that are going to be equal, I'm just counting each one of those terms twice. I'm just putting a 2 outside and going only till 2 power n minus 1. Okay, again this will follow just with a moment's thought of why this is true. Now here is the part where I'm going to apply Tannery's theorem. First, observe that limit capital N going to infinity of n sine x by n. Okay, this is just x. This is just x, which you can just see by rewriting this as sine x by n divided by x by n times x. Okay, and as n goes to infinity, this becomes of the form sine 0 by 0, sine x by x, or sine y by y as y goes to 0. So this converges to 1 and you are left with an x. Okay, so now what you do is you set n equal to 2 power n, 2 power small n, and x equal to 2k plus 1 pi by 2. Okay, and you apply this as you take n to infinity in this expression. Okay, just take n to infinity in this expression and do term by term limits and see what happens. Okay, so when you do that, you will get 1, which is what we started off with. We just started expanding 1. That's just going to be 8 by pi squared summation k equals 0 to infinity 1 by 2k plus 1 the whole square. Okay, so what I have essentially done is I have gotten a series. I have got that this series sums up to 1. Okay, then I take n to infinity. That expression will still be valid because the finite sums are all 1. Therefore, when I take it all the way to infinity, I'll still have this. Okay, then what I'm doing is I'm taking the limits essentially inside. Instead of I want to do limit n going to infinity here. Okay, I'm just taking the limit n going to infinity inside and using this observation that sine x by n as limit n goes to infinity is just x, where n equal to 2 power n and x equal to 2k plus 1 pi by 2. Under these settings, I'm just taking the limit inside, and this part is where Tannery's theorem is used. Okay, the fact that I can take this limit n going to infinity inside is justified by Tannery's theorem. Please check, I'm being a bit fast simply because this is the end of the course. You should be really good at such manipulations. So take limit n going to infinity inside, take the limits, and this is valid because of Tannery's theorem. So it's your job to check that the hypotheses in Tannery's theorem are all satisfied in our situation. So ultimately, when you do all these manipulations, which is just going to be a few minutes of work, you will get the identity. So to be extra careful, I will draw this box correctly. So we don't have a perfect rectangle, but no issues. So we have this identity. Okay. Now from this, it follows easily that summation 1 over n squared, n running from 1 to infinity is just pi squared by 6. So finish the proof. Okay, so this is a very clever and somewhat difficult proof, simply because it isn't clear exactly how such a proof was thought up of. This is from a paper and the author has not mentioned exactly how he has managed to come up with this proof, but nevertheless this is one of the simplest proofs of this identity that I could find. Of course, the one key fact that makes this proof a non-elementary proof is that you need to know Tannery's theorem for this to be true. To see this proof, you need to know Tannery's theorem, but we have already done Tannery's theorem in this course, so I thought, why not present a proof that uses stuff that we have already studied. Okay, so this finishes the proof. This is a course on real analysis, and you have just watched the module on the Basel problem.